Everything in our universe has its size. Planets are big. Insects are small. People are somewhere in between. Everything has its place in the grand order. But does it have to be this way? Does size really matter? Wouldn't it be better if everything were bigger? After all, big animals live longer than small ones, and studies show that tall people are more successful. So why are things the size they are? And what if we could change that? Using the latest science, we are going to do the ultimate thought experiment. We are going to increase the size of everything, and that includes us, to see whether a bigger world really is a better world. We're going to discover just how much size matters, how it defines everything. You'll never look at yourself or your world the same way again. You might think this looks like an ordinary house on an ordinary sunny morning. In fact, you are looking at a parallel universe. One just like our own, but with one important difference. In this universe, we can change the size of things, just to see what happens. We are going to follow a normal guy, going about his normal day, and see what happens to him when we increase the size of stars, planets, and living things. We'll find out if the way things are is the only way they can be, and explore the consequences of a world where things are bigger. Call it a thought experiment if you like. Something scientists have always used to explore the workings of the universe.
Thought experiments are vitally important for science because with thought experiments we have a way to quickly explore the realm of possibilities before we then engage in very detailed calculations. So whenever we start any question in science, we begin with a thought experiment.
By changing the size of things, we are going to explore the laws of nature and find out if there are limits to how big things can get. It's a thought experiment that will give us a deeper understanding of how things work in the real world. And we are going to begin by changing the size of planet Earth itself. With a mass of 6 billion trillion tons, that's a 6 followed by 21 zeros, the planet Earth is only the 5th biggest of the 8 planets of the solar system. Let's compare her with number 1, mighty Jupiter. Jupiter is 11 times the width of Earth and has 318 times the mass. What would life be like on a Jupiter-sized Earth? And would it even be possible? We're going to take things slowly and start by gradually making Earth bigger until it is twice as wide as it was. By growing the planet, we are going to find out how much its size really matters. Our infrastructure, roads, bridges, and buildings are all tailor-made to fit the current Earth. So, it's no surprise they won't cope if the planet starts slowly growing towards the size of Jupiter. But they're more resilient than you might think. Bridges, at least, are designed to expand a little. So it'll be a few moments before everything falls apart. Roads can be rebuilt, but the most important consequence of changing the size of a planet is far harder to work around, and that's gravity.
Gravity is the key force that governs the universe and nature on the largest scales. And at very basic levels, every object in the universe is attracting every other object according to its mass. The more mass, the stronger the force of gravity.
As the planet continues to grow, Earth's gravity will get stronger. The first casualties would be low Earth orbit satellites. Even if their orbits grow in proportion with the Earth, the planet's higher gravity would soon pull the closest down into the upper atmosphere. Then, atmospheric drag would do the rest. Falling satellites are just the beginning. But what does higher gravity mean for humanity? What would be the effect on our bodies, our health? And how much more gravity can we take? As you will see, higher gravity is a big challenge. There are a few people who actually know what life on a bigger planet feels like because they've experienced something just like higher gravity, G-force. To do his job, Royal Air Force Typhoon pilot Mark Long has to deal with extreme G-force.
G-force is like an increase in the gravitational effect. Your arms feel heavier. You find that breathing's a little bit more difficult because you're working harder against the force that you wouldn't normally be exposed to. So it's like gravity, but just more intense.
Today, he's flying a display routine which will push him and his plane to their limits. As the plane turns, Mark is pushed into his seat by G-force. Albert Einstein's equivalence principle tells us that the effect on his body is just like higher gravity, so that what he experiences during some maneuvers feels exactly the same as being on a higher G planet.
So I've just bottomed out from a looping maneuver here, and I'm turning the jet into a barrel roll maneuver. It's quite slow, so the G-force is around 2.5 at this point. And as I get towards the bottom maneuver, it starts to increase.
Back in our parallel universe, Earth is now twice as wide as it was. That means the planet's circumference and the gravity at the surface have also doubled.
So 2G actually feels all right. You can look around fine, you can move your head, but everything is just a bit more of an effort. Moving around under 2G conditions would be tiring. Life would be very slow, you'd be lethargic, moving, your legs would feel heavy. You'd just take longer to do stuff, and you'd feel tired at the end of every activity you tried.
Our infrastructure destroyed, humanity brought to its knees. A mere doubling of the radius of the planet could be the end of days. But we're not finished yet. As this is a thought experiment, let's just say that everyone survives and rebuilds to suit 2G. It's a world in which standing up is to be avoided.
If I was lying down, now the heart hasn't got to work so hard and life would be a lot easier. The distance between your heart and your head is the most crucial thing in the vertical sense because your heart has to pump the blood against gravity. So the best physique is actually fairly muscular, quite short.
It turns out the upright human design doesn't deal well with higher gravity. Had our planet been bigger, we might never have evolved. Unfortunately, 2G world has yet more pain in store. Changing the size of Earth upsets the cosmic apple cart. Our moon Moon sits in perfect equilibrium with the Earth.
If you make the Earth twice as large in radius and 8 times more massive, it has a dramatic effect on the Moon's orbit.
The Moon would be pulled into a strange new orbit that would pass much, much nearer to the Earth. Not close enough to hit, but you'd soon see the difference. But this Moon also has a dark side. In its normal orbit, the Moon causes tides in our oceans that are seldom more than 10 meters high.
If we had tides operating with this Moon coming very, very close to the Earth, then in fact the heights of the tides would be extremely high. So obviously there are some cities around the world, many cities in fact, which would become uninhabitable under those conditions because you'll have these great big tidal waves sweeping around the planet.
With the Moon now passing so much closer, tides could be up to 1,000 meters high. But so far, we are nowhere near the size of the largest planet in our solar system. But just what is the limit for the human body?
Doing 350 miles an hour at this point, and the jet is accelerating all the time. So I'm going through 4G, 5G, up to 6G as I turn onto the crowd line. At 6G, I don't think the human body would be able to function on a bigger planet. It would be incapacitated. You would just be spending your whole time trying to fight against the G-force. You wouldn't be able to do anything. In fact, you'd probably spend your entire life lying down.
But lying down won't help with what happens next. Because when the Earth reaches half the width of Jupiter, something very strange happens. The air itself becomes toxic. As the increasing gravity of massive Earth pulls the atmosphere closer to the surface, the oxygen is more tightly packed in. There are more and more oxygen molecules inside every lungful. That may sound like a good thing, but oxygen is a highly reactive element. We are designed to cope with a certain amount. Too much of it can cause violent seizures, eye and breathing problems, loss of consciousness, and eventually, death. So even the air we breathe depends on the size of the planet. And we're not finished yet.
I'm preparing my body right now for this onslaught of G. So as soon as I enter that turn, I'm at 9G. I can barely move my head, so I'm forcing my body against the edge of the seat to look round for my reference point ready for pitching up for the loop. When I pitch up for the loop, I know there's going to be another 9G maneuver, so I've pre-tensed my body, and now as I get to the top of the loop, I'm relaxing into the G-force. I've had the Typhoon up to 10.4 G, and it was painful. And I would hate to be on a planet that's at 11 G. In fact, I'd look for a different planet.
As the planet nears the size of Jupiter, insects and other invertebrates will cope better with the higher gravity than humans. But that won't help with what happens next. With gravity now 11 times what it was, the Moon would be pulled from its orbit.
So if you make the Earth 11 times bigger, which is essentially the size of Jupiter, the Moon can no longer go around the Earth anymore. It will crash into the Earth, and it will crash into the Earth in about 3 hours from the point where you actually increase the mass of the Earth.
The Earth's gravity is now just too strong for the Moon to stay in orbit. The result would be catastrophic. Life as we know it could not survive on Earth the size of Jupiter. Size connects every part of our universe. changing the size of one thing can affect almost everything. So, it's time to put the planet back to the size it was. If we can't change the size of the planet, how about changing the size of life on the planet? Living things come in a huge variety of sizes. But can we make them bigger? Will giant hearts and lungs still work? Will giant legs still support us? The answer is that it depends. When it comes to living things, size works in mysterious ways. Take insects. As animals go, we think of them as small. Even the very biggest insects weigh no more than 115 grams and have wingspans no greater than 28 centimeters. But 300 million years ago, insects were much, much bigger. Take Meganeura, a dragonfly-like insect with a wingspan of 3/4 of a meter. Is there a reason history can't repeat itself and giant insects like Meganeura take to the skies once more? Well, in fact, there is. Insects don't have lungs like we do.
Insects breathe through tiny little openings in their body, so-called spiracles, which connect to even finer tubes called tracheoles, which permeate the entire body. So this network transports oxygen to each and every single cell and removes carbon dioxide.
It's a system that works well, but only for small bodies.
You might think of the way that insects breathe as letting oxygen sink in through their tissues. Now that's fine for everything that's very close to their body surface, but it becomes harder and harder to reach structures that are deep inside the body. And if you become larger and larger, you have more and more volume relative to your surface area, and therefore it becomes harder and harder to actually reach the structures that are deep inside your body.
If the way that insects breathe limits their size today, why were they so much bigger in the past?
300 million years ago, the oxygen content in the atmosphere was a lot higher, around 1.5 times as high as now. So we now have about 21% oxygen concentration, and it used to be 30 to 31%.
In today's atmosphere, insects this big just can't get enough oxygen to function. Insects today have to be small to thrive. They have already reached their size limit. But for other living things, the rules are different, and some people are already making giant happen.
My twin brother and we live and breathe pumpkins. We always have done.
These two men have devoted their lives to making pumpkins into giants.
When Ian and I were little kids, we took one of these seeds and we planted it before we went on holiday. And since then, we haven't stopped. That was 42 years ago, and it's just our total passion, really. The seed they're like racehorses. We can look from year to year and you can see they get a pedigree in the end. You know that this seed in particular will grow lots of pumpkins to £2,000.
It's a competitive business, and the brothers put plenty of time and money into their passion. But however much work the brothers put in, there's one thing that limits how big a pumpkin can get. After around 100 days, pumpkins are genetically programmed to stop growing as their skins thicken and harden. So growing the biggest pumpkin is all about speed.
It's physically got to grow that fast. So next year we'll be putting the heating up at night to 22 degrees. We need to get this thing growing faster than 57 pounds a day. So we need to get it going as fast as we can. And it's just getting everything perfect and speed, really. It's a nerve-wracking time for us. You know, that's a year and a massive amount of work.
The biggest one, yeah? I told you.
Yeah, that's good news. A bit more. Whoop. Done. Good job. We need to get the world record, and we're getting close to it, and we've grown some big ones this year, so we'll see how we do. Hopefully our season's going to get rewarded with something good.
If it works for pumpkins, why can't people move up the scale to challenge the blue whale, the biggest animal of all time? Perhaps giants of legend could be made a reality. If two men can make a pumpkin 200 times as big as a pumpkin should be, surely we can make a human just 3 times normal size, 5 meters tall. Not a real giant, but way taller than any human has ever been before. A human being 5 meters tall may look possible, but they would be doomed to fail. To find out why, we need to go to Turkey.
When I go to a hotel or to a friend's, the biggest problem is finding a bed I fit in. The standard bed is just 2 meters. I usually put 2 beds together.
As well as having oversized feet, Sultan Kösen has an oversized pituitary gland that has produced too much human growth hormone throughout his life. As a result, he is tall. 2.51 meters tall, to be specific, which makes him the world's tallest man. Being this tall comes with perks, but also problems. He keeps breaking his legs. Sultan has travelled from his hometown to Ankara to visit his doctor.
Şimdi 4 ay önce olan kırık şu bölgedeydi. Şurada çivinin başı hissediliyor hatta. Burada. This is the femoral fracture that has occurred 6 years ago. It was a mid-shaft fracture which has displaced all the fragments, and this long rod plug has been inserted with nails to stabilize the fragments. There's a significant relationship with the length of the bone, because you know that if you apply a force on a very long rod, you can easily break it. If it is relatively short, it's not so easy to break it because of the physical properties of the bone.
Sultan's other problem is more practical. Like our 5-meter human, he keeps falling over.
He cannot walk as we walk. That's his basic problem. That's why he is so prone to easy falls.
Boy önemli değil, yeter ki insanlar
Size doesn't matter. What matters is health and overcoming obstructions.
yılları aştıktan sonra
When obstructions are overcome, it doesn't matter whether you're short or tall.
Sultan's health issues reveal one of the main problems faced by large living things. Something we will need to understand as we begin to make bigger humans. A 5-meter human would be even more likely to break their legs than Sultan. But why? To find out, let's make this statue bigger and see what happens. You might think you'd just get a larger statue, but you'd be wrong. There's something else going on. Let's try again and find out what. By the time it's double the size, the arms weigh 8 times what they did, but are only 4 times as strong. But why is that? The statue's weight depends on 3 dimensions. So if you double the height, the weight goes up 8 times. Strength depends on cross-sectional area, which is just 2-dimensional. So it doesn't increase as fast as weight. The result? Arms that fall off. So if you want to double the size of a statue, you'll have to re-engineer it to be big. Just ask Venus. She knows all about it. So, if we're going to make bigger people, we'd better do the same and re-engineer the human body. But how? There are plenty of other living things that have managed to make it to the bigger end of the scale. What can we learn from them about building a giant human? The tallest living things on the planet are coast redwoods, to be found in California.
I love these trees because of their massive size, their old age, and because of the way they build the forest that they do.
Professor Todd Dawson and his team of scientists have studied every inch of these trees. Right to the very top. If anyone knows why they're so tall, it's him.
So redwoods are a remarkably long-lived tree, and the coast redwood can live more than 2,500 years. Because they're plants, they're constantly growing. And because they're very old, as long as they keep growing and they have that old age, they're just going to keep getting bigger and bigger and bigger. So a tree like the one we're standing next to here, it probably weighs thousands and thousands and thousands of pounds, many tons. One of the things that we notice about these trees as they grow is they begin to add more at the base. So you go from a very small tree that just goes right into the ground, like a carrot in the earth. And as they grow larger and get heavier and heavier and heavier, they begin to buttress, they begin to add mass at the base because they have to have a way to support themselves. 8 meters, 5 centimeters. Nice sized tree. They sort of build some sort of a structure like an elephant's foot, if you will, at the base. Remarkable set of compensation mechanisms.
So, is this the limit? Or could we imagine a parallel universe where the biggest of living things could be even bigger? The redwood's strategy of shape-shifting, getting more triangular as they grow taller, means that their trunks could support the weight of taller trees. But they'd hit another problem.
So one of the factors that limits how tall trees get is their ability to get water to the very top of the tree itself. And while a lot of trees may stop their growth, redwoods have a special way of dealing with that water limitation as they get taller. For example, we've got leaves that come from the lower part of the crown, and these much smaller leaves, they come from the very top of the tree. As the leaf area goes down, the amount of water used goes down as well. So they become more thrifty in their water use at the top of the tree than they do at the bottom of the tree.
Moving water upwards several hundred feet needs pressure. Fluid migrating into the roots pushes water up, while at the leaves, sunlight causes water to evaporate, leading to low pressure, which pulls water upwards. The redwood's smaller leaves at the top mean only a small amount of water has to go all the way. But grow a redwood too tall, and not even those special adaptations can solve the water supply problem. The leaves would dry out and die, and the tree would go no further. Despite their problems getting water to the top, trees still show us just how big you can get if you change your shape as you grow. That means that bigger creatures can't just be scaled-up versions of smaller creatures. They need profound adaptations to overcome the challenges of size. Take a dog, for example. This dog's skeleton makes up 8% of its total body weight. But if we want to make it bigger, we'll have to beef it up a bit. 3 times the height, thicker bones mean a skeleton that weighs 10% of its body weight. But if we want to make it bigger still, we've got to overcome yet another problem. Big animals have less surface area per kilogram of weight than small ones, so they have proportionally less skin to lose heat from. This means they can overheat. Elephants evolved to be large so that they could dominate their environment, be safe from predators, and reach food more easily. But they also needed a way to avoid overheating in a hot environment. Elephants don't just have large ears because they look good. They also help them to regulate heat.
Billy, our 8-year-old, is being very energetic right now, but we're still seeing, because of the colder temperatures, his ears are much colder than the rest of his body. So it really shows how efficient they are at controlling their body temperature by using their ears. In the summer times, we would see the opposite. Their ears would be much warmer. The veins would be full of blood, using as an air conditioner, helping cool down the rest of the body temperature.
Maybe our giant dog could learn a lesson from his elephant cousins. Grow a pair of bigger ears to increase surface area, and lose the fur, since hair traps heat. With stronger bones and a way to keep cool, we can safely make an even bigger dog now. But how big can we go? How about as large as a medium-sized dinosaur, which is just big enough to run into another problem? It's just too slow. Hervé Bocheron is a paleontologist who knows exactly why big animals are so slow.
Large animals have an issue with distance. The signal has to travel along the nerves. Of course, if you are already about 20 meters long, the signal has to be both ways, and therefore it's already a significant fraction of a second that takes time for the signal to travel, and therefore the reaction time of big animals will be slower than the reaction time of smaller animals, and this will make a difference in their life. So today, for instance, the largest land animals are elephants, and it has been observed that elephants have to be quite careful when they walk, because the signal has to travel quite a long distance, and when they hit something with their foot, for instance, it takes a couple of milliseconds to reach the brain, and therefore they have to wait until the signal comes back to know if they have hit something with their foot before they make the next step.
Being slow is not good news for a dog, which needs to catch prey. A giant dog might starve to death, unless it has someone to feed it. We've managed a dog, so it should be straightforward to scale up a human. First thing to remember is that a human just 5 times normal height would weigh 125 times normal weight, so you would need much thicker bones. Then, of course, he'll need big ears like an elephant to get rid of all that heat. But before our giant gets any bigger, we have to face one challenge that most big animals don't. Humans walk on 2 legs. Hervé Bocheron is studying another primate that tried to get giant in the past. It's a story that begins in an unusual place.
It started in a Chinese pharmacy in Hong Kong, where a paleontologist was looking at what is called dragon teeth. Among these fossil material, there were some fossil human teeth, but also teeth that were much bigger, looked like humans. And these were the first discoveries of Gigantopithecus.
They weren't dragon's teeth. They were teeth from the biggest ape to ever live, Gigantopithecus.
Estimating the size of an animal based on just teeth and lower jaw is a difficult thing, but we can say that at least it was twice as heavy as a gorilla. So the weight could be up to 500 kilograms, which is a maximum estimate.
That makes it the largest primate that has ever existed. But estimating its height is even harder.
Most probably, it was not standing so much because with such a heavy weight, it was probably essentially quadrupedal. And therefore, it's more a comparison with a gorilla who is mostly walking on four legs rather than walking erect.
Gigantopithecus was just too big to stand tall like a human.
We have many examples in the past of animals that started bipedal and had to go back to their four legs. And when they grew bigger, it means that they had to carry their weight on four legs and not anymore on two legs.
So as we continue to grow our giant human, should he walk on all fours like a Gigantopithecus? Perhaps not.
If it's going to be a giant human, it has to be bipedal, because bipedalism is the thing, the one major thing that sets our genus or our group, the hominids, off from all of the other primates. We are habitually bipedal.
Being bipedal has upsides. Your head is raised so you can see danger further away. And you can reach higher to get food. But for humans, perhaps the biggest evolutionary advantage is that it keeps your hands free for other things. But the bottom line is if it's not on two legs, it's just not a human. So if we're going to make a giant bipedal human, that means we have to support all that weight on just two legs.
If you're a giant and you're really, really tall, well, you've got to get that blood pumped away from the heart and up to the brain. Very important. So you need a big pump, a big heart, and that means a big chest to put the heart in. And it's got to go uphill. And so I might put the heart higher up within the chest.
The heart is just a simple pump that has to get blood around the body, and pumping uphill is harder work. So a giant human needs as short a distance between heart and brain as possible. The chances are, however large his heart, our giant human would be lonely, and not just because of the way he looks.
Another consequence of being large is that the population will be small because each one needs a lot of food. And so giants would probably not be very numerous.
Even with a four-legged friend, life as a giant would be no fairy tale. It would have to be a very strange creature indeed to overcome all the problems that being big creates for a human being. That's because size is intrinsic to everything. Your size determines what shape you are, how you live, what you eat. Change it too much, and you simply get a different species. So, let's put things back to how they were. We've changed the size of the Earth and everything on it, and it really didn't work. But there's one last thought experiment we can try. Because if we're going to change the size of things, we can't miss out something massive that lies at the very heart of our solar system. The Sun, our nearest star. But when it comes to stars, does size matter? Size is crucial to the work of astrophysicist Volker Brom, because the size of a star determines how it behaves.
When you think about stars, then size is absolutely essential, because you could say that the size of a star, or more precisely, the mass of a star, is destiny.
If a star's size is its destiny, just how big is ours? Well, it's 109 times wider than planet Earth and 330,000 times as massive. It accounts for 99.86% of all mass in the solar system. As it turns out, just the right size for life on Earth.
The sun is, for us, the essential star. The sun really provides us with a perfect cosmic environment to enable life on Earth.
How do we know the sun is so perfect? One way to find out is to visit our parallel universe, make the sun bigger, and see if the world survives. Let's start by imagining our sun, but with exactly double the amount of gas. You might imagine it would be twice as bright, but you'd be wrong.
How a star reacts to increasing the mass is highly non-intuitive. So you double the mass and you increase the energy output tenfold.
On Earth, the effects would be staggering.
The equilibrium temperature on Earth would go up by a significant factor, so we would have a much hotter Earth, which would then suddenly become completely inhospitable.
First, the ice caps would melt. Then the oceans and rivers would dry up. The surface of the Earth would eventually stabilize at over 200 degrees centigrade. But all is not lost. There is one way we could get things back to normal.
A key question in modern astronomy is that we think about the region around any star where life in principle could be sustained.
For life as we know it to exist, the temperature of a planet needs to be right for water to exist as a liquid. The area around any star where this could happen is called the Goldilocks zone.
You basically have a very, very special region around any star. And this Goldilocks zone of not too hot, not too cold, what we call the habitable zone, is a very precious, precarious zone, because if you play with the conditions in the central star, everything changes.
As a double-mass sun burns so much hotter, this means the Goldilocks zone is now further away. 3 times further away. So we just need to move planet Earth to its new resting place, well past Mars, 450 million kilometers from the bigger sun. Here, life would not be in immediate danger, but it's far from ideal. The new longer orbit means a year is much longer. And so are the seasons. In fact, winter would last 16 months, which would make growing crops very difficult. So could Earth survive around an even bigger sun? Before we can answer that, we need to know just how big stars get. Since mankind first invented the telescope, we have wondered just how big the stars really are. This is what we found. We think of our sun as pretty big, but in the universe's Hall of Fame, it's just a nobody. The biggest star by radius that mankind has ever observed is known as UY Scuti. It's more than 1,700 times the width of our sun. But there are stars even bigger if we look far enough away. Not just in distance, but in time.
In astronomy, we have a great privilege. We can do something that historians and archaeologists only dream of. We can directly take images of the distant past. And we do this by looking at objects that are far away in the universe. objects that are far away, they have sent out the light that we receive billions of years later, and light travels with a limited speed, the speed of light. And therefore, looking far out into space means also looking far back into time.
When they looked far enough away and far enough back in time, scientists found that the biggest stars to ever exist were born in the very early universe.
If one thinks about the early universe, then you also discover possibilities of really pushing star formation to the extreme.
Professor Volker Braun has built theoretical models that show just how big these early stars could have been. His visualization lab simulates how massive clouds of gas in the early universe collapsed to form giant stars.
So there are special regions in the universe where conditions are ripe that you can have extraordinary large clouds of primordial gas collapsing in one go, if you like. So then we have a very, very extreme case of, if you like, star formation. 1 million solar mass cloud collapsing in one go. And again, this is a very special condition, and we believe this only could have happened in the early universe.
Volker's work tells us that back in the early universe, there may have been stars 1 million times more massive than our own. Far, far bigger than anything around in the modern universe. Our sun would just be a speck compared with this. The question is, could the Earth survive orbiting a star that is possibly the biggest object that has ever existed? Let's find out. As the sun grows to the size of a supermassive early star, it would envelop the inner planets. So the Earth needs to move to a safe distance. To the outer edge of our solar system, far beyond Neptune.
Then we would have our planet sitting out at this huge distance, and you can also ask how long would then one orbit take? And then you would calculate that one orbit would roughly take 30,000 years.
Not great for getting birthday presents. And New Year's Eve would be something to be enjoyed only once every 1,200 generations. But there's a twist in this tale that means none of that really matters.
The big problem then that such a hypothetical planet would encounter is that the host star, the supermassive star, would have a very short lifetime, because our sun lives for another 5 billion years, but the total lifetime of these supermassive stars is just a few 100,000 years, maybe up to 1 million years. So this is, in astronomical terms, a blink of an eye.
Put simply, if our sun had been a massive early star, life as we know it would never have existed. Before life had a chance to evolve, the star would come to an end, perhaps in a most spectacular way.
If these early superstars were to explode in a supernova explosion, and we could say that these would be the biggest explosions ever to happen in the history of the universe since the Big Bang. The Big Bang, of course, would still beat everything else. But otherwise, those would be truly colossal explosions.
In their lives, and even in their deaths, these giant early stars were the limit, the very end of the scale of big. But they just don't work for planet Earth. We've tried changing the size of the planet, the size of our sun, and even the size of living things, but nothing works quite as well as what we started with. We are our size. Change it, and we risk changing who and what we are. So does size matter? What do you think?
It matters hugely. It depends on what you're looking at. If you're looking at the brain, yes. If you're looking at bodies just sustaining life in different thermal habitats, so size matters tremendously.
Yani boy önemli değil.
Size doesn't matter.
Gerçekten ben kısa
I've met the shortest people in the world and also some of the tallest.
Bayanıyla da tanıştım yani ve uzun farklı insanlarla da tanıştım.
I even once met something taller than me. It was a giraffe.
Bir şey gördüm, o da zürafayı gördüm.
Today, Ian and Stuart produced a pumpkin weighing 2,252.3 pounds. That's a new UK record.
Size is the only thing that matters. Don't have to be pretty, don't have to look nice. Only thing that matters is size.
So size definitely matters for the redwood forest. I think it really creates the structure, the scaffolding that makes the redwood forest such a beautiful place to spend time.
So despite what some believe, bigger isn't always better. Bigger is hotter, weaker, more dangerous. Bigger is grander, slower, and more fantastic. And size really does matter.